Hello, I'm Kevin Kwik. I'm a master's student of computer science here at Cal Poly Pomona, presenting in the problem-solving category. The topic I'm presenting on is a potential covert channel of communication in the IEEE 802.11 RTS CTS mechanism. So just as some background information, IEEE 802.11 is the specification that defines the family of technologies that we refer to as Wi-Fi. Now, there are cases where it can be advantageous to transmit data covertly without it being noticed. This is usually done through what is known as a covert channel of communication. This type of communication is often done using means that were never intended to be used for communication. I'll get into this a little later. The uses for this communication are fairly broad. These are some examples I found from recently published works in the past 2 years. One suggested covert channels for sharing secrets between two devices for the purposes of increasing security. Another suggested a covert channel for maliciously exfiltrating information out of a network without being detected. And this last one didn't really specify a specific usage scenario except for general data transmissions. So as you can see, the exact purpose of a covert channel is very generic. It's just a method of communication. What you do with that method is up to the person using it. It can be used defensively or it could be used offensively, maliciously. The more interesting thing is how these channels are established and created. The first example suggested encoding information in the supported rates that a client advertises. This is known as a covert storage channel. It's called that because we store data within the bits of the network message itself. The second example encodes that information based on how much time elapses between sent messages. This is known as a covert timing channel because information is hidden within the timing of the network message. The third one is another covert storage channel hiding information within the MAC address field of a certain network message. There are advantages and disadvantages to both options, but that is a little out of scope for this presentation. The specific covert channel I'm presenting about is a storage channel that can be created within the RTS CTS mechanism of 802.11. So what does that mean? Well, let's take a step back. In a modern hardwired Ethernet network, cables connect devices together. Both devices can transmit at once because the cable they're communicating over has separate lines for transmitting and receiving. Wi-Fi doesn't have that advantage. Wi-Fi uses radio waves to transmit, and of course radio waves aren't isolated from each other. If you're in your car listening to the radio, someone in the car next to you can be listening to the same exact radio station. And if someone else were to start transmitting on the same frequency as that radio station, the two signals would collide and interfere with each other. So this is true of Wi-Fi as well. It is a shared medium. You want to avoid having two devices transmitting at the same time. The RTS CTS mechanism is designed to help avoid these what are known as collisions. This here is a simple flow diagram that illustrates its usage, and this is another simplified diagram showing the devices involved. So a device will create whatever data frame it wants to send over the network. It then listens for a little bit to see if anyone else is currently transmitting on the network. If another device is, it will wait a little bit and then it will check again. Once it sees that it seems like the network is a little quiet, it will send an RTS message, and it will send the RTS message to the access point. This message is sent to the access point. On a home network, this would likely be your router. RTS stands for request to send, and its naming is pretty literal. It is a request from one device to the access point to get permission to start sending it data. The access point can then reply back with a CTS, or a clear to send message, which is essentially giving the device permission to start sending its data. So you can see by having devices request permission to send, you can hopefully reduce the chance that two devices will transmit at the same time and drown each other out. So hopefully you will avoid that collision. The idea behind the covert channel I'm talking about is to repurpose these RTS and CTS frames for our own usage. You can see in the top right of the poster there's a diagram of a normal RTS and CTS frame. For the most part, we can ignore the frame control, duration, and frame check sequence fields and focus for the RTS on the receiver address and the transmitter address. So the receiver address is the recipient of the RTS, which is the access point, and the transmitter address is the address of the transmitter, which is the device on the network. The CTS has similar fields that we can ignore: frame control duration and frame track sequence, and it only has a receiver address, which is the address that is the recipient of the CTS, which in this case is the device on the network that sent the RTS originally. In the proposed covert channel, we modified the RTS's transmitter address and the CTS's receiver address to contain customized payload instead, which we can see illustrated in this diagram here. The data we put in these fields is limited to the 48 bits, or 6 bytes of a normal MAC address. The first byte of a MAC address contains information that indicates whether an address is unicast or multicast, and whether it is globally unique or locally administered. This involves the setting of the 2 least significant bits. So we reserve the first byte to contain this information. The next byte is used as an ID for the specific message sent in the covert channel. And this can be used in bidirectional communication to clearly identify a response to a previous message. Finally, we have 4 bytes usable for a payload of information. Theoretically, either the space for the ID or the space for the payload could be increased by 6 bits because we've set 2 of the bits in this 1 byte header, but that leaves 6 bits unaccounted for. So theoretically it could be increased slightly. Using this mechanism, we can establish either unidirectional or bidirectional communication. In unidirectional communication, the RTS transmitter address will contain a custom payload. The received CTS may copy back the data payload as if it were just a normal MAC address. In this way, the data the sender wants to transmit can be received either by an access point or by any other device on the network that is listening in and is aware of the covert channel. For bidirectional communication, the device can send an RTS with a payload, and the access point can respond back with a CTS containing a different payload. Of course, because a CTS frame is only ever sent in response to an RTS frame, if the access point wants to send a message to the device, it must wait until it is prompted by the device with an RTS of its own. Some challenges facing this covert channel are the reliability of sending data. 802.11 frames are on the data link layer of the OSI model, which is to say they are at a low level of the network stack. And at this level, there is no guarantee of reliable transmission of data. Thankfully, this is an issue that is already accounted for within the RTS-CTS mechanism, so addressing it shouldn't raise any alarms. In the normal operation, if the device that sends the RTS does not ever hear back a CTS, it simply waits and then sends another RTS. And so just by mimicking this behavior, we can attain some data reliability while not looking too suspicious. Another challenge is that RTS and CTS as a mechanism are not really as prevalent as they once were. Some enterprise networking equipment has settings to either disable RTS or only send RTS for transmissions above a certain threshold size. There are reasons for this that are again a little out of scope, but suffice to say, excessive amounts of RTS or CTS frames being sent over the air could draw attention, which is not ideal for a covert channel. In addition, if communication is bidirectional, then the transmitter address field of the RTS and the receiver address field of the CTS won't match, because the RTS frame contains one payload and the CTS frame contains a different payload. If someone notices this discrepancy, it could also attract attention, because in the normal RTS-CTS mechanism, they should be exactly the same. For this reason, it is probably best to use this covert channel sparingly and avoid sending large amounts of data. In addition, sending data unidirectionally would avoid the second issue of the address mismatch.